Hi, I wanted to talk about the Laplacian mesh deformation and how you could use that to not only deform a mesh, but also deform an animation in this case. We will go through the basic step of the mathematics behind Laplacian deformations, and we will see how we can grow the system of equations with more constraint, up to the point that it will be useful for animations also. Laplacian deformations, first thing I will do is import my libraries. And when we talk about the Laplacian, it's a system that works on a graph. And so what we will have is that we will define a mesh as being a bunch of vertices connected through edges. And that could be seen as a graph, basically. And my vertices will be in R3 because I'm XYZ coordinate in 3D dimensions. And I will build a Laplacian matrix using the normal descriptions that says that basically the Laplacians is the degree matrix minus the adjacency matrix. And what are those? The adjacency matrix says which vertices is connected to which vertices. So if I have 5 vertices inside of my mesh, I will have a matrix of 5 by 5. And for every vertex that are connected, so if my vertex 2 is connected to vertex 3, it means that in my matrix, at row 2, column 3, I will have a 1, and at row 3, column 2, I will have a 1 also. So basically just saying which vertices are connected to which one. And the degree matrix is a diagonal matrix that in the diagonal just has the number of connections a vertex has. So if my vertex number 0 has 5 connections, it means that in position 0, 0, I will have 5. And the Laplacian is computed by just doing the degree minus the adjacency matrix. So for instance, I will have these functions that compute the degree matrix from the adjacencies, because that's fairly easy to just sum the rows to see how many connections you have. And I have a little function that generate a Laplacian. It's just a strip mesh with all the edges making squares, and that's it. So all my vertices are a bunch of squares connected together. And it will compute for me, it will return the Laplacian, the adjacencies, and the vertices. And I have a big functions that just draw any mesh you throw at it. Just by giving him the list of vertices and the adjacency matrix, he can draw it in the in 3D. So if I just display this functions, you will see that I will have the generate Laplacian, and I can draw, and it'll give me this strip I've just generated with my function. So why do we talk about the Laplacian coordinates? It's basically what we're interested in doing is to be able to deform a mesh, but keep all the little deformations between the vertices, to keep it the same. So try to deform the mesh as global, but keep the details. And the Laplacian coordinates are the delta of your vertex. So if you know the position of all your vertices, what you do is that you take, for each vertex, you check all the vertices that are connected to it through an edge. You make the average of that, and you do your vertex minus that average. So the delta is just knowing how much offset you have between your positions and the average positions of all your neighbor. That's the Laplacian coordinates. And why we computed the Laplacian matrix, it's because that formula could be written as a matrix multiplication. It's just the Laplacian matrix multiplied by your vertex, and that gives you the deltas. What we want to do when we deform now, as I said, we try to deform the mesh as a global, but we also try to keep the little difference as close as possible. So what we want to do is to say that the delta vi prime, so the deform delta mesh, is as close as possible as the deform delta mesh originally. So even if I deform my mesh, all the little details, I'm trying to make them stay the same. So that's what we try to do as an arrow functions. We try to say the difference between the deform mesh and the original mesh is as small as possible. So what you try to do is to minimize that error. And if you write it as matrix formulations, that means that we try to minimize these functions. And if I try to minimize these functions, this means that because it's a square, it's fairly easy. It just means that I need to take the derivative of that function and set it equal to 0. And basically, because a bunch of conditions on the shape of the Laplacian matrix, you could actually simplify this down to say, what we're trying to solve is just to say that the delta vi equal delta v, and that's is a system of linear equation, because LV is known, it's my delta, L is my big matrix of coefficients, and V prime are the position of the vertices I'm looking for. So that's a linear system of equations, and I can solve it through a least square system just as is. So for instance, I take my functions, I do L dot V to get my delta, and I just give that to a least square solver saying that I get the Laplacian as A, and I get the position of my vertex as B, or my delta, sorry. But deltas are in 3 dimensions, so actually I have to solve for x, y, and z separately. So that's what I'm doing here, x, y, and z separately. And if I don't give them anything else, it just tries to find the best solution with all the deltas, and it has no other info. So what happens is basically, it's useless in this case, but it just recentered the entire mesh in 0, 0. So that's just saying solve the Laplacian while there is basically nothing to solve. So what we want to do is to grow that system and says, but there is a bunch of vertices that I want to anchor in some positions. So what you do is that you grow the system by having all the Laplacian on top, and then you grow the matrix with all the constraints you want to add. And in this case, the constraint is just saying, I want this vertex, number x, to be in that position. So it's mandatory, that one needs to be there. So that constraint functions is just saying, for every vertex that I will want to lock, I will make a row of zeros for every vertices that exist, and I just put a 1 in the vertex I'm trying to lock. And then the D there will be the true positions of the vertex I want to have, because that's what it does. It says vertex number 5, for instance, will be in 0, 0, 0. That's it. So that's what I will be doing here. I will build a matrix that will be the length of all the vertices that exist. And I will just set that my first constraint will constrain the first vertices. And the second constraint will constrain the last vertex. And then I will have the positions for those 2 vertices that I want to force. And that's it. I grow my system by stacking the 2 matrices on top of each other, and I concatenate the 2 deltas and the positions. And then again, I solve for x, y, z. And now we get what I asked for. I basically said I want to pin the first vertex here and the last vertex over there. And you see you get a nice curved shape. So it works for 2, it works of course for 3, and so many, as many anchors you're trying to solve. It tries to minimize the amount of errors of everything, so it tries to minimize the error of the vertices and the Laplacian deformations at the same time, which is why you get this shape here. Now, I've solved everything using the least square solver from SciPy. Basically, if you try to solve normally a least square, there is the pseudo-inverse that you could use, formulations. So instead of, if you have an a dot x equal b, which is exactly what I have, I get the L dot v equal delta, so it's the same formula. And if I try to minimize the square distance of that, the formulations through a bunch of computations, you could derive this formula here that would say that you get the A transpose A equal X equal A transpose B. And so that's something that you could solve directly now. It's not a least square problem anymore. The dimensions of those 2 matrices matches, so you could do a true solve. So if you wanted to do a solve, usually what you do is that you inverse your A matrix and you multiply your b by it, and that give you your x. So that's how you solve it numerically. So what I will do is that I will build this matrix to show you and solve it using a solver instead of a least square solver now. So basically, I've done exactly the same. I've got my A and right-hand side. And so I do the A transpose A, and I do the A transpose B for the X, Y, and Z separately. Again, I do have to do it separately for the 3 dimensions. And what it gives me is exactly the same answer. There is no difference. The only difference is that I haven't done a least square now. I've done the solve through matrix multiplications. The issues usually with this formulation, because that kind of work, and in this case it works, is that it's not numerically stable if the system is big or if it's not exactly solvable. So that's one way of formulating it, and there is another way to do it, is to do the Moore-Penrose pseudo-inverse. Basically, again, without going too much in details, it will allow you to solve these issues by replacing the A transpose A inverse by the Penrose pseudo-inverse that goes through a singular value decompositions, and that's way more stable to solve this kind of stuff. So now you could solve it just by doing, so as before, compute my delta, my A, my right-hand side, combine all of them, and instead of doing all the different math, I will do the pseudo-inverse and the Penrose inverse from the NumPy or SciPy libraries. And it works also. It will give you, again, exactly the same answer, but this one is way more stable numerically. Now, be careful that it looks like I haven't solved X, Y, Z separately. It's just because in NumPy and SciPy, all those dot products are multidimensional. So it did solve X, Y, Z, but it did it in parallel for me and returned it X, Y, Z parallel. But it was still solved separately. It still solved X, Y, and Z separately. Now, one thing you've noticed, and I said it quickly, what it tries to do here, it tries to solve for all the constraints we gave him. So we told him you have to make sure that your Lagrange multipliers, your deltas, stays as close as possible, and you have to try to make sure that you pin your vertices while I ask you to do it. The only stuff is that is trying to minimize the amount of errors that all of that is bringing. So you could see that it hasn't pinned the vertices where I asked him to do it. It minimized the amount of error, but it was not perfect. If you ever need your vertices to be pinned exactly at some places, you will have to go through another system of solving to say that you want to solve for the Lagrange subject to a bunch of constraints, which is what we will want to do here with the Lagrange multiplier this time. And so normally the basic problem of the Lagrange multiplier says that you're still trying to minimize a least square problem, but it's subject to a bunch of constraints, which is the case of what we have here. We have still LV minus delta that we're trying to minimize, but the anchor positions are constrained. The Lagrange formulations for this problem, it says that you could add those two together and inject in the middle a bunch of Lagrange multiplier there. So it's the same formulations. You just get the Lagrange multiplier in the middle. And now if you try to minimize these issues, what you have to do is to take the derivative with respect to x, and that gives you these formulations, and you need to take the derivative with respect to the Lagrange multipliers that give you those formulations, those functions. And so all of that can be turned into one big linear system, and the one big linear system is this one now, is the ATA C transpose, and then the C in the bottom, the zeros. So basically that's the first line here that you're trying to solve for A transpose B, and the C with the D here. So it's all mapped into one big system. Again, you see the formulation we had before, A transpose A, A transpose B, but you also grow it with a constraint transpose and constraint and all that kind of stuff. And if you solve this system now, it would be exactly the same problem, right? You get the L transpose L. You get a bunch of 0 blocks, and that this one you get the constraint. So you make a block matrix with the L transpose L, the constraint transpose, the constraint, and a bunch of zeros there. And then you could solve it now. It's not a least square, it's a real solve. Just to be careful that you've solved for x, but also for the Lagrange multipliers, which I don't need. So I'm only reading the vertices. That's the only part I need. And so now if you solve it this way, your anchors are constrained, and so they are really mapping it 0, 0, exactly the positions you wanted. So that's going through the KKT system from the Lagrange multiplier. So we've seen how to solve the Laplacian, seen how to constrain the Laplacian if you wanted to make it really constrained. Now there's one other thing that I've done every time is that I said I've solved for x, y, and z separately. And that's true. The L.x is only for 1 dimensions. What we want to do now is to say, could we solve for x, y, z at once? And so that we could do by growing the system of the Laplacian matrix using the Kronecker product. And if you do this, basically what happens is that I will try to grow my system by multiplying with an identity matrix of the size 3, because I have 3 vertices. And what will happen when I do this is that if I had 5 vertices and I get values, A, B, C, D, for instance, and E, if I go up to there, but let's say I have A, B, C, and if I multiply it by the Kronecker product, basically I will have now my matrix that will grow 3 times in the row and the column dimension. So instead of having A, B, C, I will have A, 0, 0, B, 0, 0, C, 0, 0. On the second row, I will have 0, B, 0, but 0, A, 0, 0, B, 0, 0, C, 0, and then 0, 0, A, 0, 0, B, 0, 0, C. So it makes the A, B, C diagonal every time. And by doing so, it gives me the same values, but on a bunch of different rows. And so what I can do now is that instead of having my x, y, z as being x, y, z and versus second x, y, z and so on, I can actually stack them with a transpose. So I can have x, y, z, x, y, z, x, y, z, x, y, z inside of one big vector, which is what I'm doing here with the v. I get the x, y, z, x, y, z, x, y, z. And so I get one line for the x, one line for the y, one line for the z, and so on. So you grow the entire system, and you do the same for your anchors, of course, and for your positions. So you grow everything the same way. The only thing I will do here is that I will actually do something I haven't done so far. I will add a weight to the anchor, and by changing the weights, you could decide how much of the Laplacian needs to be solved, how much of the anchor needs to be solved. You could start to tweak values depending on each of the different stuff. So that's what I'm doing here. I give an anchor weight of 3, build my Laplacian matrix as before. Now I just have an identity matrix. I do the Kronecker product from the L. I multiply my delta now with a flattened version of vertices. So I will have x, y, z, x, y, z, x, y, z deltas. I do my anchor, also grow it. And I also flatten my anchors. And I multiply the weights of the anchor and the position by the weights. And that gives me some constraint on how close I want the object to be. And now I still have the same results, The only difference is that I've solved for x, y, z in one pass. Instead of having solved for x, and then y, and then z, now I have solved for x, y, z at once. And I could do it for more vertices, more anchors, and so on. And why am I interested into solving x, y, z at once is that now I could start to think about constraints that would act on x, y, z at once and not act separately on a bunch of dimensions. And one of the constraints we will be interested into adding into the system is to be able to say that we want to lock some edge. We want to say that some edges are not allowed to change. And so for this, what we will do is that we said that we will have some edges before modifications and after modifications, they need to stay exactly the same length. So this is the same problem that we had when we said the deltas needs to stay the same. Now what we have to say is that the distances, but the length of edges have to stay the same. And so what we have now is that we'll have the HV, and the H is an edge incidence matrix. So it's a matrix that would say that's the two edges that are connected together. And the thing that you do is that you put one vertex equal to 1 and the other vertex equal to -1, because what we want to make sure that if one moves in one direction, the other needs to move in the other directions to keep the length of an edge the same length. And the functions for knowing the length of the edge is this one here. It depends on the rest pose of the original length you had and the current length you've computed. Now, the issue we have is that this formulation says that it depends on the distance of those edges. And basically what it means is that the distances are computed with the square of the values. So when we try to minimize the deltas, it will at the same time update the length that will actually needs to be squared to know. And so it's not a linear system of equation anymore. You cannot solve this in one go. What you have to do is to solve it once and then check the distance you have, compute the amount of errors you had between your edge, push them in the system, solve again, and so on and so on. And so it's a system that will become now iterative to fix the length because you cannot do it in one pass. So that's what we will do here. I'll do it by growing all the system as 3D. So I get the Laplacian 3D, my delta 3Ds, my bunch of anchors, it all stays the same. And now I have my iterations here that basically will compute my h and the length of all my edges. And how you do it is that you compute the original length. You compute the new vector that gives you the new length. You put the incidence matrix with 1 and -1, except that as I've done directly for the anchors, giving a bunch of weights, I would do the same for the edge constraint. So I get the length that are, instead of being just a 1, they actually have a weight. So I put the weight and minus weight, and then the length you want to compute is the original length divided by the new length, multiplied by our weight factor, and you get the vector itself that multiply this. And now you don't only solve for the L and anchors, you also solve for your H. So you grow your system with all the constraints, you solve with the least square, and you repeat until you converge towards something. So what I've done here is I said I have a bunch of vertex of edges. That's the edges I want to lock. That needs to stay the same. And those edges are those 4 that are here. So it tries to keep the length of those one as close as possible as what they were before, while still doing everything else that the system was doing. And yeah, so that's the length constraint. That's one of the constraints you could add to the system. Another stuff that happens quickly when you try to do the Laplacian is this issue we have here, is that basically what I've done is that I've completely rotated my vertex there, but you could see that the Laplacian, the only thing it tries to do is try to deform the mesh, but keeping all the local translate. So it can only skew your mesh, basically. That's the only thing it did. It skewed my mesh to try to match this, and it's probably not exactly the result I was expecting with the strip when I said take those two edges there and rotate them by 90 degrees. I would not expect that shape, that S shape. What you could do in the Laplacian is grow this into a system where what you try to do is that instead of minimizing the amount of error with the deltas, you allow yourself to consider every vertex as a system inside of a transform, and it can rotate and it can scale uniformly before doing that comparison. So you're trying to say, maybe you will find a smaller error if actually you had considered that everything just rotated 45 degrees. And that's what the transform here would be. The paper that talks about this one is the Laplacian surface editing. I've let you read it if you want to go through the mathematics behind how they derive all those formulas and the matrices that we will use soon, where they come from. It's all from this paper, so from the Laplacian surface editing. But basically what you're trying to do is to figure out what the transform you could find in the delta at the same time as trying to minimize everything else. The advantage of this system is that what they found is that you could solve for every vertex. So for every delta, there is a ti, so it's a different transform per delta. What you would want to do is to solve this system that basically says A contains all those your vertices and the vertices of all your neighbor, and you stack them in the matrix like this one. And if you solve that system for Ax equal Bi, where B will be the position of the deformed position, so Bi is all the deformed positions of your vertices, Ai is all the undeformed vertices positions, and X, what will return in this case, it will return the S, H1, H2, H3, Tx, Ty, Tz. And what they are the matrix that's the component of the matrix that allow you to rotate and scale a mesh as long as the rotations is small. So it's an approximation of a rotation matrix. So the S, C, S, H1, H1, H2, H3, it all goes into that big matrix here. That is a transformation matrix. So solving this system gives you the transformation matrix that allow you to be plugged in there as a solve. Now, what is interesting to see is that to solve this, again, we get our friend formula A transpose A. So pseudo-inverse, basically, through the pseudo-inverse, we could compute those x's. And what is interesting is to see is that it depends, B depends on the deform vertices, which means that what we have now is that before we had, in this case, we had the undeformed vertices minus the deformed vertices. Now we have something here that's take into account deformed vertices minus deformed vertices. So they all talks about basically the same thing, which means that we could turn this with formulation, say the T delta I minus LV prime, we can turn it as L minus transpose delta equal V prime. So basically this stuff become my A matrix. And we don't have B's anymore here. We just have zeros. Because we've never moved it on the other side. We never have the LV equal LV prime. We moved everything on the left side, so we can jump off to the 0 to solve, and everything is regrouped here, and that give you the V prime. So the T can be just solved by solving this without taking care of the BI. And now you could solve all the system. So what it means that you have to pre-compute and solve the T's for every vertices once, and then you could solve your least square as usual. So that's what I'm doing here. I take every vertex that I have, compute that big matrix, that big A matrix with all my vertices and my neighbors' vertices. I do the pseudo-inverse that gives me the S, H, and T. I multiply my transpose by my deltas, and that gives me my new deltas. And then finally, I remove it from a Laplacian. So at my L3, I remove my deltas. And I basically now have built this matrix. Instead of a L, I have my L minus T deltas. So that's what you pre-compute once. And then you push that as your anchor, the anchor. You stack them as usual. And so the difference now is that you don't solve for deltas anymore. You solve for a bunch of zeros. That's it. You just have zeros to solve. And you do your least square. And if I do this, now you could see that I have the deformations where he found out that it was better to actually rotate every element up to reaching the direction I wanted. And it curved my shape here. And also it scaled it, because I give it something bigger. You see that the first square is bigger. It actually scaled the entire square to find out the best solution in this case. So that was the interesting stuff of this paper, is to be able to turn this into a transform issues. Now I could have the transform and on top of it add my edge constraint. And so what I will do is that I will say that I want all my strip there in the middle to keep the same length. And that's what I would try to solve. So again, I compute all the adjacencies and the L, and now I loop through my edges constraint at the same time. And what I get is this shape now. So not only has it rotated, it also has managed to keep the length of all my edges. Now what I will do is I will take all the functions we wrote, and I will make one big function I can use and reuse every time I try to do a Laplacian deformation. So those functions will be basically the fact that you could compute the rotation invariance, the transform for all the vertices, and then you get the deform that allows you to deform your mesh, choosing different algorithm, different constraints and weights and all that kind of stuff. So all of the options are inside of these deform functions now. And I can reuse this function, see to play and see what we could use, iterate through different number of iteration for the edge constraint, remove the edge constraint, remove the rotation invariance, use art constraint or hard constraint, and use edge, and so on and so on. So all the options are tweakable, and you can play with them independently. So now that I have a function that will allow me to deform any type of mesh I could throw at it, what I would do is that I would decide to start to play with animation data instead of just my bunch of vertices here. So I will load my character, load my animation, and I will pre-compute a bunch of foot contact. So I know when my foot are locked on the ground, and I would just render this so we could see what we're talking about. So we just have this character walking along, and that's what I will want to use and deform using the Laplacian deformation. So the first thing I have to do is to convert my animation into a mesh, a Laplacian mesh. And so for this, what I would do is I would take the animation And I will take a bunch of bones, and all those bones I will get the positions in wall space. And I will take the positions of each of those bones for every frame, and that will be all my vertices. So that will be the position of the bones at every frame. And then you have to build your adjacency matrix. And the first adjacency matrix you will build is the skeleton adjacencies, just saying that, yes, okay, my foot is connected to my leg is connected to my hips, and so on and so on. So that builds the connections of the skeleton, and I repeat that for every frame using the Kronecker product again to put it as a diagonal product. So my adjacency, so I'm getting from here, is basically every pose at every frame are just connected, the bones are connected between them, and that's it. Then I get another functions if I want to connect the bones together frame by frame. So connecting my hips of frame n to my hips of frame n plus 1, and my foot of frame n to my foot of frame n plus 1, and so on and so on, and a function to compute the Laplacian out of it. And what I could do is then take my animation, and I would take just a small piece of the animation that moves forward. And I get my skeleton adjacencies, I connect them all my animations frame, and I compute my Laplacian. And I will anchor the first pose and the last pose. And the way I will anchor them is that I will take the 10 first vertices, belongs to the first pose, and the 10 last vertices, they will be exactly the same pose as the first one, except that I will just shift them 3 meters in front. So that's what I'm building here. And if I display this, and I would just remove the stuff there. What you have is this. In black is the original animations, so every frame of the animation. And what you have in yellow is the deformed animations that I've done. So you could see it was nearly working straight, but just not straight. And the first and last frame were not the same. So now I've locked the first and last frame to be exactly the same, so I can have a nicer loop, let's say. Now what we could see is by default, I'm stretching the entire animation a little, and so if you could see here, all my feet were probably were anchored, and I have all the positions at the right spot, while this one now is sliding a little. I have this one is more visible. My deform mesh is sliding. So the first thing I would do is that we said I will add a bunch of length constraint. That was the reason why we wanted to have the ability to have length constraint, is because now I can add constraint inside of my animation. And all the edge constraint I will do is I will say between the toe and the foot, if there were a lock during the animation, so that's the foot tag is what I've computed as when do I have contact. If I have contact, I basically said that I want to lock the length between all those frames. So that's what I'm doing here. I'm computing the length between all those frames. And the second constraint of length I will do at the same time is that I will say what the length of the legs have to stay the same. So I will basically say that for every frame, every leg has to keep the same length, and same for the foot. So leg and foot have to stay the same all the time. So if I turn the edge constraint, you can see that everything is red, means that it's all the edge constraint I have on the system. I have a lot of them, and unfortunately it's hard to see, but yeah, let's see here, you get the constraint that is between the frames also. So I'm only displaying the skeleton, I'm not displaying all the edges, because you get more edges, you get all the edges of between the frames also. But as constraint, you can see that it is there, it's connected between them, and those ones should be zeros, so one of the constraint. So I can crank up the number of iterations it will do, just to try to solve this a bit more and make sure that when it slides, it basically keeps all the foot at the same time and moves all of them at the same time. Another way you could have done this was to not making edge constraint and just saying that all of those were the same vertex and pinning only one vertex. But it will be harder at a later stage to recompute the animations because, you know, I would not have just match for every frame, but that would be another solution to do it. The other things that I've also added is the way that I can say the height of the foot has to stay the same exactly between the original animations and the new animation. And how I've done this is just to say that instead of anchoring the vertex by itself, now that I'm computing everything as x, y, z, I'm only anchoring the y-axis, and that says all the y-axis of the foot has to stay the same. It can only move in x and z, but the y cannot change. So that's what the use feet height means, is that you pick all the height of the feet and it cannot change. And now that I have deformed my animation the way I want it, I can even crank it a little higher, see if there's any difference. Now that I have deformed the animation the way I want it, I can regenerate animation out of it. And so how I would do this is I would take the original animations and take the new vertices, the new positions, and basically I can take the original animations to know what was the orientations, and I can use all the position of the vertex now to recompute IKs, recompute orientations of the hips and that kind of stuff. So I recompute the hips orientation based on the position of the left and right leg, and the height is between the spine and the hips that I have. That gives me the new hips, and I do the same for both feet, and I compute an IK between the two. And so this allows me to recompute the animation, so I can compute animations out of the original animation and my new vertices. And that gives me this now. I have my animation that match the new deform Laplacian. So I've deformed my animations by turning it into a mesh, deforming the mesh, and turning the mesh back into an animation. And I could do all sorts of transformation this way. What I will do is that now that I have something that goes straight, what I want to do is to generate curved path animations out of this. And so I will have a function. So first thing first, I will make out the true animations out of the data. So now I have a walk straight animation. It's a real anim for me. And I have something that allows me to say, if I know that I have a path along a straight line, well, I can bend that path. So that's what this function does. If I have, where are you? Yeah. If I have a path that is straight and it points along that path, I can actually bend those points and do whatever I want with it, and I can shift them, which I'll use also being able to bend in or bend out when you're bending. And so I would take my animations, my walk straight animation now. I will convert it as a Laplacian the same way. And what I will do now is that I will anchor every single vertex of it, because I will make sure that all the vertices will bend using that curve function. So basically I'm anchoring every vertices, and what I got is, let's remove first, is this. If I start to bend, I'm bending all my meshes, and I'm still solving for the Laplacian and solving for mainly solving for the edge length. That's what will be interesting in this case, because you could see now that my feet again are sliding because of the transformation I just gave it to it. So I would recall the exact same function that says every bone has to keep the same length and every steps have to stay the same length. So that's the use edge. It has a hard time at the beginning of the few iterations, But if you start to iterate, and see that it can start to solve and figure out a curved path with the feet as locked as best as it can, and you could bend it as much as you wanted. What I've done also is that I have bend the bottom and bend the top, but shifted the top a little depending of the angle, so it has to lean in basically. And now that I have this, I could iterate a bit more, make sure that I have something fairly stable, and of course I can regenerate an animation out of it, and I get my animations of the character bending and walking along the path curved. So that's probably a bit extreme, but that's the example. So this is what you could do with the Laplacian. You could deform a mesh, and then of course if you can deform a mesh, you could try to turn your animation as a mesh and use it to deform your animations. I hope you liked it, and see you next time.